Hello, welcome. I'm James Makeley with the Rocky Mountain Smiths. Welcome to our first online demonstration. Today's demo, we're going to be putting a rivet into a set of tongs to hold them together. That is, setting a rivet. We're going to be doing this hot. But today's demo isn't really about riveting tongs together. It's about producing a certain style of rivet and the tooling to help to do that. What we're looking to do is set together a set of tongs with the rivet in it. This can be done many different ways, but we're going to focus on creating a rivet head that matches a factory rivet head. This is a 5/16 diameter rivet with a factory dome head. These are readily available, and 5/16 is a very good size for smaller and medium duty tongs. But this one, as you can see, is too short to have enough material to create the new rivet head. We'll be creating the rivet from rivet stock. We'll be creating both heads to match a factory head. So this method is useful not just for putting tongs together, but if you are working with factory-made rivets and want to match the look of the factory head in your work with the new one you're creating. This is the methods that I use to make the tooling set the rivet. This is a 5/16 diameter rivet, which is a very good size for a hinge pin for most tongs. This one is a bit short. We are going to be making them from round stock rather than using the factory head. But today's lesson is about replicating that factory head. If you want to do work where you are matching the factory head with the head you create, that's the tooling we're going to make today. Here's an example of some of that tooling for a 1/4 inch rivet. Tooling that I've made and used previously for a 1/4 inch rivet. This is the rivet set, or the punch that will create the rivet head. And this is a bolster for that same rivet that's used to put underneath while we set the hot end of the rivet. To create the matching factory head of the rivet, this one even has a logo on it. Factory dome head. We want to match this. To do that, we're going to create the tooling using ball bearings. These hardened steel ball bearings will allow us to create the tooling we need, both the punch, the rivet set, and the bolster. Now, first off, what size is this? This is a 5/16 diameter rivet. These are pretty standard, and the head diameter on it is what's important. I've got a nice little gauge here, and we will try. We are 9/16 diameter loosely with the head of the rivet, so that's what we're going to match. So we're looking for 9/16 diameter ball bearing, like so. Well, where can you get these? I found these in my local Ace Hardware. Sometimes you have to look around at a couple of them. One may carry them, one may not. Local hardware store should carry some ball bearings. If not, order them a day or two ahead on McMaster-Carr. One of the first things I've created is a simple little plate with a hole in it that matches the diameter of the ball bearing. This is actually slightly tight fit, but that is okay. The thickness of the plate is close to half of the diameter. When you purchase the ball bearings, they are hardened steel. They will be under impact when we are creating the punch on top of them. To begin with, they are fully hardened and could dimple the face of your anvil. So it's a good idea to have a sacrificial plate of softer material to put between the anvil and the ball bearing. The ball bearing will heat up and soften as we are working the hot metal on top of it. But this is one way to protect your anvil to begin with. Now, what volume of material is required to create this hemispherical dome head here? That's the big question. We need to know how much length of rivet stock is required to create this, or something very near to it. So to help with that, I created myself a handy little guide some time back. This was created for 1/4" rivet stock. However, the formula works with all round stock material. This is an example plate I created for myself to see what the look would be like, and I can match in the future. I've done 2 styles of heads, the dome style, like a factory rivet, and a pancake style, just hammered down flat. This is, the numbers here are the length of stock required to produce this particular effect is based on how many times of the diameter of the rivet stock. So in this case, we would have 2 times the diameter of the rivet stock in length gives us this much volume using our rivet set, or just the flat hammer face. 2.5 times the rivet diameter in length yields almost a complete dome head, like the factory rivet. Almost, but not exactly. So I choose to go with 2 3/4 times of the diameter. So here is our math. To create the rivet and the tongs, I will need about 2 3/8 inch length of 5/16 round. That number comes from the tongs that I'm going to be riveting together are 5/8 of an inch thick. The rivet will pass through the 5/8 of an inch, and we'll need 7/8 of an inch on stock on either side to create the 2 rivet heads. To create the first rivet head, we will be using a bolster block and putting our stock in there and heating and hammering the rivet head down to create the first dome head. Now, this is not the 7/8 that we need. We will cut it down. But when we begin, we want 7/8 of an inch here to heat and hammer down. Here I have one large heavy block I've drilled a 5/16 hole in. But if you don't have that heavy of a steel block, you can start with something much smaller. Here is 1.25 inch hot rolled steel bar. I've drilled a variety of sized holes in it. We have the 5/16, but this is not greater than our 1.5 inch that we need. So to take care of that, we're just going to put another steel block with a hole underneath, as long as we have our 7/8 sticking up here in the end to create the first rivet head. This is a leftover architectural piece. The edges were cold chamfered, but that's not necessary. It's just what I had on hand in the way of a piece of 3/4 inch square hot rolled steel. It has not been heat treated any. It has work hardened a little, but not sufficiently. Again, we drilled the little divot in the end to help us start the location hammering down on the ball bearing. Hopefully we will stay as centered as possible. Hot rolled steel has sufficient alloying material in it to harden if quenched in water, which is what we will be doing. We'll do the same with the bolster as well. For the bolster, I have started the exact same little or similar drill divot in there to help hold the ball bearing in place while it is driven into the hot steel block of the bolster. This is again another piece of hot rolled steel, just what I had on hand. Happens to be 3/4 of an inch thick. It's about 2 inch wide. Anything close will work. Let's take just a moment to talk about safety. And there are 2 aspects of safety I want to speak about. The number one is the ball bearing. Because as we're working with it, it will get hot. In being in contact with the hot metal, the heat will transfer into it. So you don't want to be handling it once it becomes hot. Make certain that you happen to have a good pair of tongs that will grasp that bearing tightly and securely. Because it wants to hop off of the anvil and things fall off of the anvil. It happens. You will see this. That is why we are working with bearing that is sitting in a hole in a metal plate to help reduce the opportunity for that bearing to go right off of the anvil. If it does, you need to be ready to catch it. You do not want it rolling somewhere into a corner where it potentially could come into contact with anything that is combustible, because it may well be above 500 degrees if it falls off the anvil. The next thing I want to talk about is working with the hot metal in the fire. We're going to be cooling the metal and handling a short piece of metal that we're working with in the fire. We're going to be cooling the end of it to hold it. But it is best to handle it in the cooling with a pair of tongs. What you do not want to do is dip it into the water and get it wet to cool it, and then grasp it with your leather glove. Because the leather glove, once it has absorbed the water it's been in contact with, loses its insulating value. You're relying on that leather glove to insulate you from what is a piece of hot metal you are handling. Not only will it lose its insulating value, but the heated metal can turn that moisture in the glove into steam, which can result in a worse burn. So keep your gloves dry, handle the metal with tongs while it is wet, or keep a rag handy that you can wipe the metal off with. We're going to begin working on the business end of the punch where we have drilled the little dimple in the end. We want to control the heat, keeping a very high heat in a very short space so that all of the work is concentrated in this zone. If necessary, we will heat and then cool the punch and then heat again so that we get a high heat in a small area. Then we'll set the punch over the ball bearing and hammer it down onto it, turning 90 degrees as we hit. And notice that I'm trying to keep the punch as vertical as possible as I do this. We don't want to be leaning back and forth. Straighten this way, over the hardy hole, hitting here, not hitting here. So here, turn, and here, because it was bent in two directions, and we do that until it is straightened out. Once it is straight, then we can proceed with finishing the socket. Alright, we're going to call this complete. Now this is not entirely on center, but it will work all right. It is relatively straight going down the punch. You will notice how much flaring you've gotten from the mass upsetting in the end of the punch. I have switched to a 1/4 inch plate with a hole in it because the 5/16 was too thick and was impeding the punch getting there deep enough. If I set it over the 1/4 inch plate with the ball bearing, I am almost touching the plate. So that's what I'm looking for. So I'm relatively close to a full hemisphere or half of a sphere in this end of the punch. I'm also relatively flat across the face. I can file the edges off after the fact. Do that prior to your hardening. So let's file and then we'll harden. Ease into the water, then move fast. Move fast, move fast, move fast, and keep moving fast. You may even hear the steel as it's going through transformation. It will whistle. Keep moving it, keep moving it, keep moving it. Eventually I put the whole thing in, and I move easier now, but I'm still moving the steel. I'm going to do this until I cannot see steam rising up off of the steel. A little longer. I see a little steam rise. There we go. No steam rising off of the steel anymore. It's gone through transformation and it is hardened. Now I had the bolster heating upside down in the fire. That way, in a gas forge. That way that the working surface was not exposed to the flame. The underside of the block was. Again, working with a heavy hammer. Keep the punch straight, or you'll ding the surface of your bolster if the punch gets off. Stop part of the way through your process and do a little flattening of the block, the bolster block from the back. And I'm pretty well there. The punch is just about touching the bolster. So that is as deep as I want to go with that. Now to begin making the first head of the rivet. We're going to heat at the base of the stock rather than at the top. We want the base to get good and hot. You can give a second for the heat to run down the shank a little, that's okay. But heat at the base. Set torch aside. We want to upset the mass slightly, not entirely all of the way. And center as close as we can above the hole. Now we will reheat. And use the punch. That is the rivet set. You may have to reheat. And we have a fairly nice dome head rivet going on. Here we have an example of a finished rivet head produced with our rivet set. There is only a very slight little amount of flashing here from being just barely over the amount of volume we needed to produce this hemisphere, but it is really, really close. And we have a good fit for our bolster. Here we have a factory-made 5/16 rivet with the dome head. We're going to use this to put our tongs together. This portion of the reins we saw earlier that the rivet just doesn't quite fit in it. We can solve that by three methods. The first is a drill bit. Simply run a drill bit 5/16 through there, should resolve that, and you'll have a good fit for the rivet. Or if you have a drift for your rivet, you can use the drift or a nice smooth and very round punch. Very carefully you can open the hole up slightly more, drift it open so that the rivet fits. We're going to use the drift here with tapered ends. Drive that through. Now we have a very nice fit for our rivet. This rivet happens to be the correct length as it is, so we're going to go ahead and use it. There is our hinge. We want to focus on keeping that material as straight down onto the hull as possible. If it starts to go off, turn it so that you can use the natural curvature of your swing to bring it backwards. This is where we will stop. We will reheat and set the rivet with the rivet set. We will heat the entire rivet. One more heat. The tongs do not have to be very hot. Heat them up in the forge. Work the rivet joint for a little bit while it's hot and quench the tongs. They don't have to be complete full quench. These, of course, are made of just hot rolled steel, and so they will harden but not become brittle in the water quench. Just be aware if you're working with tongs that are made of a high carbon or high alloy steel, it is better in that case to heat them, work the joint, and allow them to cool in the air rather than quenching them in water. And just work them while they are hot until all the visible glowing is gone and they are moving freely. And there are our riveted tongs. On behalf of the Rocky Mountain Smiths, I would like to thank you for joining our video demonstration today, and we hope to see you again in the future. Thank you.